Okay, so in this video, we are going to consider our first example of a test of hypothesis, and we are going to test here for the standard deviation. So here's the problem. A small brewery has purchased a used automatic bottle filler. The technical specifications state that the volume distributed in a bottle is normally distributed, with a mean of 541 milliliters and a standard deviation of 2 milliliters. To test whether or not the bottle filler is still calibrated, the brewery decides to fill 20 bottles and obtains a sample mean of 540 milliliters and a sample standard deviation of 2.6 milliliters. So in part A, we want to test that the specifications for the standard deviation are correct at the 5% level of significance. So as always, when you have a test of hypothesis, there are two possible approaches. There is the p-value approach and the rejection region approach. And I'll show you in this video the two approaches. They are equivalent, so you can use either one. So let's write down our two hypotheses. And we always will be assuming that H0 is valid. If you remember, H0 will be the null hypothesis, the status quo hypothesis, or the hypothesis of no change, and we will have an alternate hypothesis in H1. So the status quo here would be that the bottle filler is still calibrated, therefore that the true mean is 541, and the deviation is 2 milliliters. Since we are talking about testing that the specifications for the standard deviation are correct, so we're testing for sigma, so H0 will be that the bottle filler is still calibrated, so the deviation is indeed equal to 2 actually milliliters. And now H1 will be the alternate hypothesis, right? So the opposite of sigma being 2, and here we have three options. We could say sigma is less than 2 and have a left tail test. Sigma is bigger than 2 and have a right tail test, or sigma is different than 2 and have a two-tail test. Now if you look at the evidence, we have obtained a sample standard deviation of 2.6 milliliters. So here you have essentially here two valid options. You could either in H1 formulate that sigma is bigger than 2, or sigma is simply not equal to 2. Either hypothesis would be justified. Let's go with sigma is bigger than 2 milliliters, because the evidence from our sample seems to be supporting this fact, right? The claim is that the deviation should be 2, but we sampled 20 bottles and we obtained a deviation of 2.6, which was greater than 2. So H1, the alternate hypothesis, will be that sigma is greater than 2. So we have our null hypothesis and our alternate hypothesis. We are testing at the 5% level of significance. So this is alpha. So alpha is 0.05. And if you remember, the significance level will be the probability of a false positive. Therefore, the percentage of values that the percentage of the extreme values that we reject. Since H1 is sigma is greater than 2, we will be rejecting the 5% greater values of our distribution. But, and one other thing is n, our sample size, is 20. We have sampled 20 bottles. We don't need to write down x bar and mu because we're testing for the standard deviation, so we don't care about mu and x bar for now. This will be in our next video. As always, we need our test statistic. Since we are testing for the standard deviation, the statistic, if you remember, is n minus 1 s squared over sigma squared, and this will follow, since we are assuming by assumption that we have a normal distribution, a chi-square distribution with the degrees of freedom. And if you remember, the degrees of freedom are simply n minus 1. Since we have 20 bottles in our sample, we have simply 20 minus 1, which is 19. So we have a statistic with 19 degrees of freedom. And one thing I forgot to mention was our sample standard deviation, which was 2.6 milliliters. So S is 2.6 ml. Okay, so we have our statistic, and now let's look at the observed value of our statistic. Since we have a chi-square distribution with 19 degrees of freedom, well, what I'll usually do when we have an observed value of a test statistic, I'll write the variable, here it's chi-squared, with a subscript of OBS for observed. Well, here, in our case, n was 20, so n minus 1, as we have said, is 19, times s squared, but s was 2.6, so it's 2.6 squared over sigma, and because we are here under the assumption, we're giving the null hypothesis the benefit of the doubt, we are under the assumption that sigma equals 2, so we get 2 squared. With your calculator, if you compute this, so 19 times 2.6 squared divided by 2 squared, which is 4, you will arrive at an observed value of chi-square of 32.11. So this is under the assumption that H0 is true. So we assume that the bottle filler is calibrated, therefore has a standard deviation of sigma being equal to 2. Now, the question is, and this is the same question in every test of a hypothesis, what is the likelihood of us observing this value of an observed statistic under the assumption of the null hypothesis? And as I've said in the beginning of this video, there are two approaches that are equivalent. There is the p-value approach and the rejection region approach. Let's start with the approach of the rejection region, and this is the one that I will favor in this course. But the beginning stays the same, so we now have approach number 1. And that is the so-called rejection region approach. And the idea is, since our significance level is 5%, we will reject the 5% more extreme values, and since we have a right-tailed test, we will reject the 5% right tail of our distribution. Well, we have a chi-square random variable, so we have a chi-square distribution. So we can draw our generic picture of the chi-square distribution. Since we have 19 degrees of freedom, the chi-square will look something like this. And as we have just said, because we have a right tail test, sigma is bigger than, so to the right of 2, we are going to reject the larger 5% of values. So we will reject the larger 5% of values. And this is your significance level. Well, now we have to use our distribution table. If you remember, we had 19 degrees of freedom. So you have to figure out what is the chi-square value here, where to the right we have 5% area. So we use our table of the chi-square distribution. So let's see. The table entries again are values of chi-squared, which is what we need. And we have to specify two things, the p-value, the area to the right of the chi-square score, and the degrees of freedom. We had 19 degrees of freedom, so it's right here. And the area to the right was 5%, which is right here. So if you go down, 19 for the degrees of freedom, 0.05 to the right as an area, you see that the chi-square score is 30.14. So now we have obtained our value for chi-squared. This is 30.14, and this will give us our rejection region. Again, because we have a right tail test, sigma is bigger than to the right of 2, we are rejecting the more extreme 5% of chi-square values. So this implies that our rejection region will be equal to, well, 30.14 all the way up to positive infinity. We are rejecting the values of chi-squared ranging from 30.14 all the way up to positive infinity. And you see this interval contains the more extreme 5% of values, the larger 5% of chi-square values. And now think of it. The question is now, how do we use our observed value of chi-squared, our rejection region, to make a decision as to whether or not we should accept H0 or reject it and accept H1 instead of H0? Well, think of it. We are assuming that H0 is true. So we're giving H0 the benefit of the doubt. If H0 is true, then this interval contains the larger 5% of values. Well, let's see. We took a sample of 20 bottles and we obtained an observed chi-square of 32.11. What's interesting here is our observed value of chi-squared actually belongs to our rejection region. So let's ask what that means. We said, okay, we'll assume that H0 is true. So the bottle filler is still calibrated. So sigma is 2. We took a sample of 20 bottles, obtained a chi-square value of 32.11. And because our chi-squared value that we have observed from our sample is in the rejection region, this means that the probability of this happening is less than 5%. Because this region right here contains the larger 5% of chi-squared values. So the odds, if you take a chi-squared value at random, to fall inside this interval, to be an element of R, is around 5%. And this is what we have observed. We have observed a chi-squared value inside this interval. And so this is a really unlikely event. R contains the more extreme 5% of values. So if you have, or if you ask, what is the probability that under the assumption that H0 is true, that you observe a chi-square value inside this interval, the answer is 5% or less. And we have observed such an occurrence. If H0 is true, the probability of observing a chi-square value of 32.11 is actually less than 5%. This is so unlikely that this is strong evidence against H0. Because if H0 is true, we would have observed something that is very unlikely. And so we end up rejecting H0. And this is why this is called the rejection region. If you have an observed value of a statistic that falls inside the rejection region, this means you have a very extreme value, and so you reject H0. Of course, if we reject H0, this means that we will favor H1. So we do not believe that the bottle filler is calibrated. We believe instead that the real deviation is actually now bigger than 2 milliliters. So we reject H0, and we conclude by accepting H1. And this is the approach with the rejection region, right? The region contained the 5%, the larger 5% of values. So if h naught really was true, the probability of observing a chi-squared value inside of this interval would be 5% or less. So this is a really unlikely event, and we have observed such an event. This is so unlikely that we reject h naught and therefore accept h1. Let's solve the problem now using the equivalent second approach called the p-value approach. And I'll squeeze it here because you'll see how short it is and why it is equivalent to the rejection region approach. Personally, I prefer this approach, but choose whichever one you prefer. This is the so-called p-value approach. So again, since we had a chi-square distribution, we draw the picture for a generic chi-square distribution. And now we will look on to the real line for the chi-square values with our observed chi-square. And we have observed a chi-square of 32.11. So we imagine you draw it here, so 32.11. And now we ask, okay, how likely is it that we have observed this particular value of chi-squared? Well, if you go back, we had a right tail test. Sigma was assumed in h1 to be bigger than 2. So the p-value will be the probability of observing a value as big as the one we have or bigger, because we have a right tail test. And this will be our so-called p-value. That's the one we want to find, keeping in mind that we had 19 degrees of freedom. So you see it's the reverse problem. Here we were prescribing the area of our right tail to be 5% because we had a significance level of 5%. Here we're saying we have observed a chi-squared value of 32.11, and we are asking, because we have a right tail test, what is the probability that we observe a value as big as 32.11 or bigger? So what is the likelihood of our observation? So we go back to our chi-squared distribution. And you'll see why this is not as nice given our table. Because we knew the chi-squared value and the degrees of freedom, and we'd have to extract from that the p-value, the area to the right of our chi-squared value. So we had 19 degrees of freedom, and we have to find the closest chi-squared to our 32.11. And you see, well, at 30.14, the area is 0.05, but that's the area to the right. And because our chi-squared is even bigger, the area that we'll have will be less than 5%, right? If you move your chi-squared to the right, you actually lose a bit of area. So you see, we will not be able to get the exact p-value, but we'll have an approximation. At 19 degrees of freedom, with a chi-square of 30.14, we have an area to the right of 5%. 32.11 is bigger than this value, so our p-value will be less than 5%. That's the best we can say at this point. So from our table, the p-value, we don't know exactly what it is, but we know it is less than 0.05. And if you notice, this is actually our significance level. And now how do you interpret this? The significance level, if you think of the p-value approach, says that this is really our cutoff point. Up to what extreme are we willing to give h0 the benefit of the doubt? And then we're saying 5%. So if we observe something that is more than 5% likely, we give h0 the benefit of the doubt, and we say, let's assume that h0 is true. On the other hand, if we observe something that is less than 5% likely to occur. That is our cutoff point. We say this is too unlikely. We no longer assume that H0 is true. We don't believe in it, and we reject it. So your significance level is your threshold. Anything more likely than 5%, you would say H0 seems reasonable, let's accept it. Anything smaller than 5%, you say this is too unlikely, we don't have faith in H0, we reject it. And this is our case. We have observed a value of chi-squared, and the probability of observing a value as big as the one that we have observed, or bigger, is actually less than our threshold of 5%. So we're saying what we have observed is too unlikely under H0, so we do not have faith in H0, and hence we reject H0. And by the same token, we end up accepting H1. Same conclusion, because both approaches are equivalent. But you see, because of our table, the way it is built, it's easier to read off from the significance level the endpoint of your rejection region. So this is slightly more straightforward. And this is why in this course I will favor this approach. And this completes our first question, part A. We have to test that the specifications for the deviation are correct at the 5% level of significance. Our conclusion is that in this case, with this level of significance, we reject H0. Therefore, the claim that the bottle filler is still calibrated, and therefore we accept that the deviation is indeed bigger than the 2 that is stated in the specifications. Let's look at B now. B is quite simply, would your conclusion in part A be different? Our conclusion was that we rejected H0 if we now change the level of significance to 2.5%. Well, let's see. Everything is the same here, except now that we will have a different significance level, therefore a different rejection region. So let's figure out, with a significance level of 2.5%, what will happen to our rejection region, and see if we get a different conclusion. And this will be quite short. So again, we have a chi-squared distribution. Since we have a right-tailed test, we reject the 2.5% larger values. So 0.025 is our significance level of alpha. We had 19 degrees of freedom, and now we want to find the cutoff point here, the value of chi-squared. Once again, we can read this value from this is our solution to part B. We will read this off in our table of the chi-squared distribution. We want the value of chi-squared given a p-value of 2.5% and 19 degrees of freedom. So let's see. 19 degrees of freedom is here. 0.025 is 2.5%. And we find a chi-squared value of 32.85. So this is 32.85. And so we have our rejection region. The region that contains the larger 2.5% of values of chi-squared is from 32.85 to positive infinity. So our interval contains the more extreme, larger, because we have a right-tailed test, 2.5% of chi-squared values. And now we ask, is our observed chi-square value in the rejection region, in which case we reject H0, or if it's outside, we will accept H0. Well, if you remember, our observed chi-squared value was of 32.11. And if you notice, 32.11 is less than 32.85, and now this is a chi-squared score that is not in the rejection region. So what we said here is if we observed a value of chi-squared inside this interval, the odds of this happening are 2.5% or smaller, so it's really unlikely. And if we are in this position, we say it is too unlikely of an event, and we would reject H naught. Well, our observed chi-squared is actually not in the rejection region, so it is more than 2.5% likely, and so we end up not rejecting H naught, therefore accepting H naught. And the answer therefore to part B is yes. You see, with a significance level of 5%, we ended up rejecting H naught, and therefore accepting H1. But with a 2.5% level of significance, if we only reject the 2.5% of larger values, we end up accepting H naught. Therefore, that the bottle filler is still calibrated. So this is a great example of how the significance level may affect your conclusion. We went from a 5% significance level and rejecting H naught to a 2.5% significance level to accepting H naught. So keep that in mind. In our next video, we will consider a test of hypothesis for the mean.